Let's do another example illustrating the power of the master theorem, or the simplicity of the master theorem. So, hopefully you've all seen the simple algorithm for binary search. Let's assume that we're given as input an array of length n of sorted numbers. So the list is sorted, and we want to know, is the number k in the list? Okay, so how do we proceed? Well, we look at the middle element of the array, and we see if it's equal to k. If it's bigger than k, we're going to perform the same operation on the left half of the array. We'll recursively search the left half of the array. If this value is less than k, then we'll recursively search for the value on the right half of this particular array. Okay, so we'll let t of n be the number of operations needed to find a number in a sorted list of length n. So if we use binary search, t of n is going to be, well, we need to look at one element of the array. Okay, so we have to do kind of one operation there. We have to look at the middle element. Okay, so that's sort of one operation or one time step. And then we need to search on either the left or the right half of the array. So we need to search a list of length n over 2. Okay, so we used sort of one operation to look at the middle of the array, and then we recurse on either the left or the right half of the array. And so then we have to do t of n over 2 additional steps in order to possibly find that particular number. So the number of operations for a list of length n is the number of operations for a list of length n over 2 plus that one operation to kind of look at that one spot in the middle of the array. So here we have a recurrence, and what are our values for a, b, c, and d? Well, a here, since the coefficient of t of n over 2 is equal to 1, we have a equals 1. B is 2, because we're dividing n by 2. C is equal to 1, and D is equal to 0, because we have 1 times n to the 0, 1, sitting out there. Okay, so we have our recurrence set up, and we have values for A, B, C, and D. Let's quickly go to back to the master theorem, and I'll just copy over what our values for A, B, C, and D were. A was 1, B was 2, C was 1, and D was 0. Okay, so is A less than B to the D? Is 1 less than B to the D 1? Nope, so we're not in case 1. How about, does A equal B to the D? Does 1 equal B 2 to the D 0? Yes, it does. This means that we're in case 2. So we're in case 2. Case 2 says if A equals B to the D, which it does, then f of n is big O of n to the D log n. So here this implies that t of n is big O of n to the D log n. But what is D? D is 0. This implies that t of n is big O of log n. So you probably already knew that the complexity of binary search was order log n, but here we proved it using the master theorem for recurrences.